Okay, good evening. So this is our 32nd lecture, and in the previous lecture we have started already our discussion on non-dimensionalization of governing equations. Okay, so if you recall what we had done, we had actually taken the dimensional form of governing equations, particularly for incompressible flow situation. Okay, and then what we have done, we defined some dimensionless parameters. For example, x star equal to x by L, y star equal to y by L, and z star equal to z by L. So all the spatial dimensions we non-dimensionalized with length scale L. Similarly, all the velocity dimensions we have actually non-dimensionalized with some reference velocity capital U. Okay, and so our small u star is small u by capital U, small v star is equal to small v by capital U, and small w star is equal to small w by capital U. Okay, so this was the non-dimensionalization of velocity parameters. Once we substituted these dimensional parameters x, y, z and u, v, w in form of dimensionless parameters, then we did some algebraic manipulations, and from there we found that divergence star of v star is equal to 0, where this del star operator is nothing but divergence operator, but this divergence operator is in terms of the dimensionless parameters del by del x star I cap plus del by del y star j cap plus del by del z star k cap. Okay, so this is something which we have done, and similarly then what we have done, we have substituted this non-dimensionalization forms of the dimensional variables into our x momentum and y momentum equation, and these two equations we had got. Now one mistake I am doing over here, this was not mu, I think it was 1 by Reynolds number. Huh? Is it correct? Was it 1 by Reynolds number? So this was 1 by Reynolds number. Okay, so this is nothing but my x and y momentum equation. But what I have to do is, I have to also use the similar approach for non-dimensionalizing my z momentum equation. So once I will be doing this for z momentum equation up to the viscous term, my equation is identical to x and y momentum equations, but I have one additional term also over here in the z direction, which is particularly coming because of the gravity. Okay, so this is appearing as a body force term. So once this additional term is appearing in my governing equation, so I have to also non-dimensionalize this term as well. Okay, so once I will be doing that, I will be finding that u star times del w star by del x star plus v star times del w star by del y star plus w star times del w star by del z star equal to minus del p star by del z star plus 1 by Reynolds number times del star square of w, and now is the important term. So important term is what we have done basically, while we are converting this equation from dimensional form to non-dimensional form, from the left hand side we will be getting one term common, which is rho u square by L. So that we have to actually bring to other side. So once we are bringing this to other side, my P is becoming P star, and this mu is being replaced with Reynolds number. So in place of this also, what I will be getting, this L divided by rho u square, it is coming from the left hand side. Okay, and this I have to multiply with the body force term present over here, so which is rho times g. Is this one clear? So this coefficient is coming nothing but from the left hand side. So if I do so, my rho will be cancelling out and I will be left with, I am just writing the right hand side only, minus del P star by del Z star plus 1 by Reynolds number del star square W minus GL by U square. Okay. So if you see this GL by U square, because your entire governing equation is in dimensionless form. So if governing equation is in dimensionless form, this also should be in dimensionless. So if you check its dimension, it will come out as dimensionless quantity only. Okay. So this particular dimensionless quantity is something which is called as, any one of you know its name? What is the name of this dimensionless parameter? The name of this dimensionless parameter is Froude number. Okay. The name of this dimensionless parameter is nothing but Froude number. So you can see over here, once we have done this non-dimensionalization of our fundamental governing equations, we have got three important dimensionless parameters. The first important dimensionless parameter is Reynolds number, which is equal to rho ul by mu. Second important dimensionless parameter is P star, which has come equal to P by rho u square. This important quantity P by rho u square, when it is written in terms of delta P by rho u square, it is called as one important dimensionless quantity which is called as Euler number. Okay. And third important parameter which we have got from the gravity term, that is nothing but u square by GL by u square. So we call this parameter to be our Froude number, and Fr is written as nothing but u square by GL. Okay. Is this point clear? What I am trying to say over here, is this one clear? So now you can see that ultimately when we have non-dimensionalized the equations, now we need to simply solve equations for dimensionless velocities u star, v star, w star, dimensionless length scales x star, y star, z star, and whatever the fundamental fluid properties were there which were kind of becoming independent, these were clubbed together. So density and viscosity were the fundamental fluid properties which were individually participating in the governing equations. These were now clubbed with the geometric parameters of the flow, which is geometric parameter is L, reference length scale, and flow parameter which is velocity u. So we have now clubbed together geometric parameter, flow parameters, and fluid properties, and this combination has given us the dimensionless form of Navier-Stokes equations. And in this dimensionless form of Navier-Stokes equations, we have got actually three important dimensionless parameters which are combining these geometric, flow, and fundamental fluid properties. Okay, so first parameter is Reynolds number, whose definition is rho ul by mu. Second important parameter is Euler number, which is delta P by rho u square. Okay, and third important parameter is Froude number, which is equal to u square by GL. Now, one important point you have to keep in mind, once we are considering the just a minute, there is some issue with this screen. Yeah, so it's working now. So when we are writing our governing equations in the dimensionless form, so of course we have to substitute our boundary conditions also in the dimensionless form. Okay, so typically if you recall, what were the generic set of boundary conditions which we have to apply for solving the Navier-Stokes equation. First is, if we have any, sorry, okay, it's working now. So what I am saying is, once we are using our dimensionless form of Navier-Stokes equations, then we have to also supply the boundary conditions in the dimensionless form. So if you recall, earlier when I was talking about the Navier-Stokes equations, I had given you one generic list of boundary conditions. So what was the generic list of boundary condition? If we have any inlet or outlets, then for inlets or outlets we have to supply basically the value of velocity and pressure. So I must have the values of, now because my equation is in the dimensionless form, so I must have the values of dimensionless velocity and pressure thing known for inlets and outlets. Okay. What was the second important condition? Second important condition was presence of wall. If I have the presence of wall, then the tangential component of the velocity will be 0 because of the no slip condition. So in a similar way, I can specify V star tangential has to be 0 at the wall, and this is coming because of the no slip condition. Okay. And third important point we were having is that if I have a free surface, so what will be happening at the free surface? First is, the normal component of the free surface was, normal velocity of the free surface was equal to its profile. Okay. So W star has to be equal to del eta star by del T star. And what was the second important condition? If I have a free surface, our pressure is say PA, here pressure is P liquid, then P air minus P liquid has to be balanced by the surface tension force, which is equal to sigma times mean radius of curvature, means Rx minus 1 by Rx, and plus 1 by Ry. Okay. So this was the pressure boundary condition. So once you will be doing the non-dimensionalization, you have to also write this particular condition in the non-dimensional form. So if you write this condition in the non-dimensional form, like if you are having presence of free surface, then you can write this PA as PA divided by rho u square, or PA minus PL by rho u square. So if you are dividing this side by rho u square, here also you have to divide by rho u square. Fine, gamma by rho u square. And then this Rx and Ry, these are nothing but the radius of curvature. So radius of curvature is having length dimension. So if I have to write non-dimensional radius of curvature, I have to divide the radius of curvature with L. Like x star is equal to x by L. In the similar way, Rx star will be equal to Rx by L, and Ry star will be equal to Ry by L. So if I do substitute this, then I can write this as Rx star minus 1 plus Ry star minus 1, and this will give me one more 1 by L term over here. Is this point clear? So it means that once you are having the presence of free surface, then you can see this this has become delta P, left hand side has become delta P by rho u square, which is nothing but your Euler number. Okay. Is this one clear? Delta P by rho u square is nothing but your Euler number. So Euler number has become equal to some quantity gamma by rho u square into L times Rx star minus 1 plus Ry star minus 1. So now can you tell me what is this quantity gamma by rho u square L? What is this quantity? This particular quantity is nothing but your other dimensionless parameter, which is called as Weber number. Okay, and this will be only coming into picture if your flow involves free surface. Okay, if you are having a pipe which is completely filled with either liquid and liquid is flowing through a pipe, or say it is completely filled with air and air is flowing through a pipe, in that case you will be finding there is no presence of free surface. If there is no presence of free surface, then the term involving Weber number will be negligible, and in that scenario you will be finding this delta P for air and liquid will be actually same. So because it will not come into picture. Okay, so once we are doing the non-dimensionalization of these fundamental governing equations and the boundary conditions, we are finding some set of dimensionless parameters, and these dimensionless parameters are having some relevance. Okay, so if you compare the first dimensionless parameter, what is first dimensionless parameter? Reynolds number. So what does it is representing? Rho u L by mu. What does it is representing? It is representing the relative importance of velocity of fluid medium divided by its viscosity. Okay, what is rho times u? Something which is associated with the motion of a fluid mass. Rho is something which is defining the density of the fluid mass, and u is its velocity. So something which is associated with the motion of the fluid mass, and viscosity is something which is associated with the dissipation, viscous dissipation within the fluid mass. Okay, so Reynolds number is a parameter which gives you the relative importance between inertia and the viscous forces, because its numerator is identical to inertia forces and denominator is something which represents the viscous dissipation, because the important term which is coming in its denominator is actually viscosity. Okay, so if I say that my Reynolds number is unity, the meaning is inertia forces and viscous forces are of same importance. If I say my Reynolds number is very very small than 1, what is the meaning? The meaning is, in my problem, viscous forces are actually having dominant role in comparison to the inertia forces. Okay, if I say other way, that my Reynolds number is very high, it is extremely large. If Reynolds number is extremely large, it means inertia forces are more dominant than the viscous forces. Okay, so if my Reynolds number is very high, in that case I can get rid of this last term from my momentum equations, because if Reynolds number is large, then 1 by Reynolds number will become equal to nearly equal to 0. Okay, so it means that if your inertia is very significant in comparison to the viscous forces present in the system, then you can actually remove this last term. So that is something which we do majority of the times for compressible flow analysis, where we are having, say, airplane moving, aircraft moving in the moving in the atmosphere. So their velocity of the flow will be so high that our Reynolds number is extremely large, viscous effects are negligible, and we can actually neglect these viscous terms. Okay, so similarly, your second dimensionless number, that is Euler number, what does it represent? Delta P, change in pressure, is having some connection with the rho u square. Okay, so rho u square, which represents the, once again, the motion of the fluid particle. Okay, and this particular second number, Euler number, becomes cavitation number if, so definition of Euler number is delta P by rho u square. If you consider your delta P is nothing but P of liquid minus P of vapor, and then you write rho u square. In this scenario, we call this number as nothing but our cavitation number. Okay, because in certain scenarios where pressure of the system reaches less than the vapor pressure, then cavitation will be coming into picture. Okay, so if we are considering vapor pressure over here, then phenomena of cavitation can occur. So that's why we will be calling this as cavitation number. Okay, so cavitation number should be positive for the flow. If cavitation number becomes negative, then we will be having conversion of liquid into vapor, and we will be having the occurrence of some bubbles in the flow field. Fine. Then third important parameter which we are calling is Fr equal to u square by gl. So u square is once again representing nothing but the inertia of the fluid particle, and gl is representing actually gravitational push. Okay, force because of the gravitational pull. So when we are considering the relative importance of the gravity and the inertia of the flow, then Froude number will be coming into picture. Okay, then fourth important dimensionless parameter we have seen is our, just now I have seen Weber number. Okay, so Weber number has become, so definition of Weber number is rho u square L by gamma. So this rho u square L is nothing but representing the inertia of the fluid particle, motion of fluid particle, and this gamma in the denominator is nothing but representing the surface tension. So if I have to make the comparison in between the inertia forces and surface tension forces in a flow field, then I will be looking into the value of dimensionless parameter Weber number. Okay, so, and one important point, Weber number will be only coming into picture if in my system, if in my fluid flow analysis there is presence of free surface. If free surface is not present, then of course surface tension effect will not be coming into picture, and there is no relevance of Weber number. Okay, is this one clear? Likewise, so till now what I have done, I have only considered the Navier-Stokes equation, and then for some certain set of conditions I tried to obtain the dimensionless parameters, and then I have obtained some set of dimensionless variables. Okay, but I can have, other than these dimensionless parameters, also a large number of dimensionless variables. For example, if I talk about compressible flow, then important dimensionless parameter is Mach number. What does it represent? It represents the relative importance of speed of flow divided by speed of sound in the fluid medium. Okay, so similarly we may have to come up with ratio of specific heats Cp by Cv. This is also another dimensionless quantity which is of importance when we are talking about the compressible flow. Okay, so what I am trying to do over here, I have listed a set of dimensionless parameters, few which has come from non-dimensionalization of the basic governing equations, and few I have written in addition, because when I have done non-dimensionalization of governing equations, I have only considered the case of incompressible flow. Okay, but if I use compressible flow, then I can have involvement of speed of sound and ratio of specific heats as well. Okay, is this one clear? So likewise we may have a number of dimensionless parameter depending upon the flow problem. We have to understand and find out which are the relevant dimensionless parameter and which are not relevant for us. Is this one clear? What is the role of dimensionless parameters into our equation? Once I have non-dimensionalized the governing equations, now if I have to find the solution of these non-dimensional equations, I will be considering some value of Reynolds number, some value of Weber number, Prandtl number, etc. Okay. Okay, so now we will talk about another very important topic, which majority of the times we utilize in our fluid mechanics analysis, particularly while we go for the experimental analysis. Okay, because every time we cannot develop some experimental setup which is exactly mimicking the prototype of a device. So if you talk about aeroplane, if you have to find out what are the drag and lift forces acting on an aeroplane, so one way is you develop the whole body of the aeroplane of its exact dimensions and then allow the gas to air to flow over this. Okay, that way you can do. But what we have, this dimensional analysis also helps us in providing some sort of similarity laws, and by taking the help of similarity laws, what we can do, we can develop the model of a prototype, and whatever the analysis which we want to perform, instead of performing over the entire prototype, we can actually do this analysis only on the model. Okay, but when we will be applying the similarity laws, before applying similarity laws, we have to ensure three fundamental conditions which must be satisfied between model and prototype. So first one is called as geometric similarity. First condition is geometric similarity. Second condition is kinematic similarity, and third condition is dynamic similarity. Okay. So when we talk about geometric similarity, say first I will be talking about geometric similarity. So when we talk about the geometric similarity, say I have, this is the wing of a aeroplane with its exact dimensions. Exact dimension means, say it has some length equal to LP, some width equal to WP. Okay, so this is I am calling a prototype. I can say that this prototype will be geometrically similar to a model airfoil. Sandeep, you have not taken speech. So geometric similarity meaning is that I can say this is geometrically similar to a model only if all the dimensions are scaled by same parameter. Okay, so the meaning is, if I draw corresponding to this large scale prototype a small model of aerofoil over here. Okay, so now say if I say this small WM is width of the model and L M is length of the model. Okay, so if I am saying that my LM is nothing but LP divided by alpha, then WM should also be equal to WP by alpha. Then only I will be able to ensure the geometric similarity. Is this point clear? So for geometric similarity, all the length scales, all the corresponding length scale or commensurate length scales between model and prototype must have same scaling parameter. Okay, for example alpha over here, I am saying that length of model is equal to length of prototype by alpha, width of model equal to width of prototype by alpha. Other than this, there should be identical shape. Shape also should be identical, because if you scale all the dimensions with reference to a common parameter, then ultimately your shape also will be the the same. Okay. Now third important point can come. You can consider that, say you have a rough surface. You have some rough surface of the airfoil having some roughness of 1 micrometer. So for ensuring geometric similarity, what should be the corresponding roughness on this model? Please tell me. What will be the corresponding roughness? This should be once again 1 micrometer divided by alpha. Okay. Now let's consider, say in your model at some point of time you have used some rivet. You have used some rivet to join some plates on the airfoil body. So when you are considering the size of this rivet on the prototype, if you use a corresponding size of rivet on a model, this size should also be scaled with alpha. Is this point clear? If you have any nut bolt which is protruding out of the surface of the body of the prototype, when you are developing a equivalent model, then the size of that fastener, nut, bolt, anything, that should also be scaled with reference to the size of the body. Is this point clear? So this is how, if all these criteria are satisfied, then only we can say that our model and prototype are nothing but geometrically similar. Is this point clear? Another important point we have to consider over here, we get the idea of some point over here which is typically called as homologous point. What is the meaning of homologous point? Say if on my model I have some point over here, okay, then on my prototype also I could have, on my prototype if I have some point over here, then on my model also I must have the point at the identical location with scaled parameter, with scaled length. Okay, so with identical location, if I have same point over there, then only my situation will be geometrically similar. Okay, and that will be only possible if I am scaling each and everything with the same parameter. Is this point clear? So these 2 points, this green triangle on model and green triangle on prototype, these two are nothing but can be called as homologous points on the model and the prototype. Is this point clear? So this is first type of similarity which we have to ensure while we are considering the model and the prototype, which is called as geometric similarity. Second similarity is called as kinematic similarity. Now, once I am saying that my model and prototype are satisfying the kinematic similarity, so along with the scaling of length parameter, I have to now also consider the scaling with the time parameter. Okay, so I have to bring into picture now time parameter. My time parameter should also have the similar scaling. So if ultimately time parameter is having the similar scaling, then my flow parameter will automatically come into the picture. Okay, so fundamentally I can say that if homologous points have same velocity at homologous times between the model and the prototype, then we will be calling that our situation is kinematically similar. Okay, how I can define this? There is a simple idea. Say if I consider that I have flow of inviscid fluid over a body. I have some circular body and inviscid fluid is flowing over this. Okay, so this is say my prototype. If I have to develop its corresponding model, then of course model will be of smaller size. Say this length was LP, and this length dimension is LM. So one important point is that LM will be some alpha times or LP by alpha. Fine. Now what I am saying over here, I am saying that I have nothing but the flow of inviscid fluid. Okay. So when I am talking about the inviscid fluid, then ultimately for this type of flow situation, which one is relevant dimensionless parameter? You will be easily recognizing Reynolds number. Okay. But once we have simply said that flow is inviscid, the effect of Reynolds number has vanished. Now we need not to consider because viscosity is not playing any role. Okay. So it means in this situation I don't have any dimensionless parameter over here which is actually dominating other than just the scaling of length parameters. Okay. So the meaning is that if I consider say V1P as my flow velocity for the prototype at this point and say V2P as the flow velocity at these 2 points, then for model if I say I have at the homologous point, okay, the meaning of homologous point is the point at the identical location when this is scaled with reference to a common length parameter. So if at the homologous point I consider that my velocity is Vm1, then at other homologous point if I consider my velocity is Vm2, then if my Vm1 is some parameter beta times of Vp1, then Vm2 also must be equal to beta times of Vp2. Then only I will be able to ensure the kinematic similarity. Is this point clear? Homologous points at homologous times must have the homologous velocities. Then only we will be able to ensure the kinematic similarity, and always to satisfy the kinematic similarity we have to take help of some dimensionless parameter. But for this situation, because I told you that we are considering inviscid flow, as our flow is inviscid, so because of that Reynolds number is not coming into picture, so we are saying some arbitrary parameter beta is actually scaling my velocity field over here. Okay. Now I give you slightly different situation. If I say that I have free surface flow, okay, if I have free surface flow such as I have the presence of some surface waves at the interface. So of course when I will be considering prototype, say my height of wave is hp, wavelength of the wave is lambda p. Okay. On contrary, if I consider its prototype and say flow velocity is Vp, if I consider its equivalent equivalent model, say this is my equivalent model of this, which has amplitude of waves as hm, wavelength of waves as lambda m, and velocity of flow as Vm, and say we have presence of gravity over here. Okay. So I am not interested in the minute features of the curvature, but I am interested in say the relative importance between gravity and the flow inertia. Okay. And when I am shifting from this prototype to this model, say all my length dimensions like hm equal to hp by lambda. So for ensuring geometric similarity, I must have lambda m equal to lambda p by alpha. Is this point clear? Up to this point, anyone is having any confusion? Now, if this free surface flow situation is there, and I told you that I have the relative importance in between the gravity and the inertia forces. So if I have relative importance between gravity and inertia forces, it means my Froude number is playing a significant role. Okay, so if my Froude number is playing significant role, then if I have to ensure the similarity, then Froude number for model must be equal to Froude number for the prototype. What is the definition of Froude number? V square by GL. So Vm square by G times Lm equal to Vp square by G times Lp. G will be cancelling out. From here I will be getting V model by V prototype equal to square root of Lm by Lp. What will be this? You can see Lm by Lp is nothing but 1 by alpha. What is Lm by Lp? 1 by alpha. Okay. So this I will be finding alpha times minus 1 by 2. Is this point clear? So my Vm by Vp has become nothing but alpha times minus 1 by 2. If from this velocity, now I know the scales of length, okay, length scale is alpha and scaling of velocity is alpha power minus 1 by 2. From this, can you tell me what will be the time scaling between model and prototype? What will be Tm by Tp? Time equal to velocity by length. Okay, so I can write Tm by Tp as velocity by length means Vm by Vp times Lp by Lm. So Vm by Vp is alpha power minus 1 by 2 into what is Lp by Lm? Alpha. So time is also scaling with alpha root square of alpha. Okay. So the kinematic similarity means, the meaning of kinematic similarity is we have to basically have some scaling in between time and length such that we have the same velocity scales for homologous point between the model and the prototype. Point is clear? Okay. Now third important similarity which we have to satisfy when we do the model and prototype analysis, this similarity is something which is called as dynamic similarity. Okay. So the fundamental idea of dynamic similarity is that the forces on a particle in model and prototype must scale with the same scaling parameter. Okay. For example, if I consider, say, I have some reservoir and fluid is flowing through this reservoir. So if I consider arbitrarily any point A in the prototype, and if I say for this point my force triangle is something like this, this is the pressure force acting on this, this is the gravity force acting on this, this is the viscous force acting on this, F mu. So my resultant force will be the inertia force, because then only my criteria of force will be satisfying. So this is my, say, inertia force, which is the resultant force in this force triangle. Okay, this is my prototype. If I consider the equivalent model, of course model will be having very small size, and if at this point for the model at point A I calculate the forces, if this is the magnitude of Fp force, this is magnitude of Fg, this is F mu, and this is F inertia. So all these forces are for model and these forces are for prototype. So the scaling of all the forces and their directions must be same. Directions must be same and the magnitude of all the forces should be scaled equally. Fine. Now if we have to satisfy this dynamic similarity for compressible flow, first let's talk about incompressible flow. For incompressible flow, dynamic similarity can be satisfied if and only if my Reynolds number of model equal to Reynolds number of prototype and Froude number of model equal to Froude number of prototype. Okay, and other than this, if you say that for you are having incompressible flow but surface curvature effects are also important. So if surface curvature effects are also important, then which number will be coming into picture? Weber number. Okay, so then Weber number of the model should also be equal to Weber number of the prototype. Is this point clear? If you have some phenomena where cavitation is also important, though flow is incompressible, but cavitation is also important. If cavitation is also important, then our Euler number, or we can say cavitation number, should also be equal. Fine. For ensuring the dynamic similarity, cavitation number should also be same. So the basic idea is that we should first identify that for our flow problem, what are the important dimensionless parameters. Okay, and these important dimensionless parameters we have to make equal, then only our dynamic similarity will be satisfied. Fine. One important, okay, now if you have compressible flow, then of course Reynolds number we have to satisfy, but along with the Reynolds number, what other parameters we have to satisfy? For compressible flow, another important parameter is Mach number. We have to satisfy that Mach number of the prototype and model should be same. Second important parameter, ratio of specific heats, Cp by Cv. This ratio should also be the same. Okay, but you will be finding that in majority of the cases, geometric and kinematic similarity are easy to satisfy, but from practical conditions point of view, you cannot always satisfy the dynamic similarity. That is one very important issue between the model and prototype, and to avoid that issue, then we have to go for some sort of extrapolation of the data. Okay, how? That I will show you with the help of one example. Say if I have one incompressible flow situation, what I have one incompressible flow situation, and in this incompressible flow situation my gravity effect is also important. Okay, so first thing, for satisfying my geometric similarity, I have to consider that all the length dimensions of the model should be equal to length dimensions of the prototype divided by alpha. Is this point clear? This is the first point. Second important point is, if my incompressible and gravity both are coming into picture, then Froude number is the important parameter which can give me the scaling between length and velocity scales. Because if length and velocity scales are satisfied, then my kinematic similarity is ensured. Okay, so immediately I must attempt to equate Froude number of the model equal to Froude number of the prototype. Is this one clear? So if I do so, then V model square by GLM will be equal to V prototype square by GLP, and just now we have seen that Vm by Vp from this will be coming out as alpha power minus 1 by 2. Point is clear? Is this point clear? So it means that my velocity scales are actually being scaled with this power. Now, in order to ensure the dynamic similarity, I have to also satisfy another parameter, that is Reynolds number must be equal to for model and prototype. Okay, so RE model equal to RE prototype. Then only we will be able to satisfy the dynamic similarity. Other two conditions have satisfied the kinematic similarity. Okay, so what I will be doing out of this, rho m Vm into Lm divided by mu m rho p Vp into Lp divided by mu p. Now what I can do, I can divide this density, I can divide mu by density, so ultimately it will be becoming kinematic viscosity nu. So I will be getting Vm Lm by nu model. Nu is nothing but kinematic viscosity, dynamic viscosity by density, and Vp Lp by nu p. So from here I will be getting that nu model by nu prototype is equal to how much? Lm by Lp times Lm by Lp times Vm by Vp, correct? What is Lm by Lp? Alpha power minus 1. And what is Vm by Vp? Alpha power minus 1 by 2. So it means that my viscosity of the model, whatever the fluid which we are using with model, its viscosity should be 1 by alpha times of 3 by 2. Is this one clear? What I am trying to say over here? Okay. So now, important question comes, if I say my alpha is 0.1, alpha is 0.1 means my model is 10% scaled version of the prototype. All the dimensions are reduced, are taken as 10% of the prototype. If alpha is 0.1, how much is coming this model? Viscosity model, please tell me. What is 1 by 0.1 power 3 by 2? So it means that, simple meaning is that, say whatever this value is coming out, the simple meaning is that whatever the prototype is there, of course prototype will be with the actual fluid, real fluid. Say if I talk about a turbine, so turbine is using water as the fluid medium. If I talk about aircraft moving in the air, then air is my prototype fluid. So in these scenarios, my kinematic viscosity of water or air, which are the generally used fluids, their kinematic viscosity is becoming the prototype viscosity. Okay, but if I consider the kinematic viscosity of model fluid, that will be coming some arbitrary value. So what we have to do, if we have to ensure the perfect dynamic similarity, then I should get that particular type of fluid over here. Okay, so when you are using only say 10% of your length for the model, you will be finding that your model fluid viscosity is coming very low, extremely low. Okay, so in reality, if you consider, if you use water at the one side for prototype fluid, and if you use mercury as some other real fluid which is existing in the nature as your model fluid, you will be finding that viscosity of mercury, kinematic viscosity of mercury is only 1/9 of the kinematic viscosity of the water. Okay, so you will not find some fluid which is actually having the value which can ensure your dynamic similarity. Is this point clear? So in real scenario, you cannot satisfy the condition for a model fluid which can satisfy your dynamic similarity. Okay, because some absurd value of the property will be coming, and that particular fluid you will not be having its existence in reality. If still some closed fluid is existing to that absurd value, then also that fluid will be having some challenges. So every time whenever you are scaling the prototype from water, then you will be finding some low viscosity fluid for model analysis if you have to ensure dynamic similarity. But the low viscosity model liquid existing is say mercury. If you use mercury, it's too expensive and it's not good for health. You cannot use mercury in the open space for model testing. Okay, because vapor of mercury is not good for health. So there are certain challenges. Because of that, whenever you will be doing the model and prototype analysis, you will be finding all the times that your say Reynolds number of model is actually smaller in comparison to required for ensuring dynamic similarity. Is this point clear? Because viscosity of model has to be low, but if in your model you are not using that hypothetical fluid and you are using your generic fluid water only for the model also, then ultimately your viscosity condition is not satisfied, and whatever the Reynolds number you will be getting for model, because you are using high viscosity fluid now, that will be smaller in comparison to required for ensuring dynamic similarity. Is this point clear? Because of this, if any parameter, say coefficient of drag, you are calculating for model. So Reynolds number of the model I consider on the abscissa. Say if I get some trend something like this, so you will be expecting that this is the range of measurement for model, but actual expected range would be high Reynolds number. Okay, because your model viscosity was low to ensure the dynamic similarity. So say this is my desired range of Reynolds number. So what I have to do? I am only able to do the experiment in this range, but my desired range is actually high. So if desired range is high, what I have to do? I have to extrapolate this data. Okay. So once I extrapolate this data to the desired range, of course this extrapolation will not be error free. I will be having some sort of errors also associated with this. So I must put some error bar also along with this. So this is the bound across which I can say that my model and prototype have the accuracy of testing. Is this point clear? So whenever you will be further say studying your courses like uh, design of these energy devices or energy conversion devices, etc., where you talk about turbines, pumps, etc., there you will be doing uh, more analysis on this model and prototype testing. So there you will be finding that sometimes ensuring the 100% dynamic similarity is not possible, So we have to go for some sort of extrapolation, and whenever extrapolation will be coming into picture, then of course there will be some sort of errors associated with that analysis. Is this point clear? So this is one big benefit of the dimensional analysis, which helps us in theoretically creating the complete similarity between a model and prototype. But in practice, when we go, then we have to actually sacrifice our actual theoretical accuracy, because we cannot obtain the hypothetical fluid which can completely satisfy the dynamic similarity. Okay, now quickly we will do one numerical problem and then we will end up our discussion on this dimensional analysis. Okay, so this is the problem. So what we have is the pressure drop due to friction for a flow in a long smooth pipe is a function of average flow velocity V, density of the fluid rho, viscosity of the fluid mu, and pipe length L, and say diameter of the pipe is D. So delta P is given as function of all these parameters. We wish to know how delta P varies with velocity. So our interest is, it means our output parameter is delta P and input parameter is velocity, but along with that input parameters there are other involved parameters also. But our major interest is to see the variation of pressure with velocity. Okay, so we have to use the pi theorem, Buckingham pi method, to rewrite this function in dimensionless form. So what is our first task? What is the first task? Please tell me. First task is, it is given in the question that delta P is function of velocity, rho, mu, length and diameter. Okay, we have to write it in the dimensionless form. So can you tell me all these parameters, how many number of fundamental dimensional variables are being involved? J will be equal to 3 for this case. Is this point clear? If J is 3, it means what we have to do? We have to find 3 repeating variables. What we have to do? We have to find 3 repeating variables. Let's consider the 3 repeating variables are density. Okay. 3 repeating variables are density, diameter of the pipe and viscosity. Fine. If I consider these 3 as repeating variables, these are not forming any dimensionless group. So it means I can consider these 3 as the repeating variables or scaling variables. Okay, what will be my dimensionless groups? Pi 1 will be first dimensionless group, that will be equal to rho times A, D times B, mu times into, say, delta P. First parameter, let's consider delta P. Now you tell me, what will be the final value for pi 1? I have already done a lot of practice in the last 2 lectures. Please calculate pi 1 and tell me how much will be pi 1. First you tell me pi 1. In the meantime, let me write pi 2 equal to rho times A, D times B, mu times C times velocity V. Then also tell me what will be value of pi 2, and third parameter is pi 3 equal to density times A, D times B, mu times C times, and final thing left is L. Calculate the values of ABC for each situation and then tell me what will be the final values. What is pi 1? What is pi 1? Anyone calculated pi 1? Any one of you? This is the difference actually. Whenever you start doing, then it is the real test. We have been doing the similar thing in the last 2 lectures. Anyone calculated pi 1? Otherwise this lecture will continue till you are not calculating all pi 1, pi 2, pi 3. I should shift all my classes to evening hours. So you are solving in mobile phone. Someone got or not yet? Have you got? What you are thinking then? See, this is very simple thing you are not able to calculate. So, and same thing happens in the exam. That is why out of 30 class average is 5.13. No issue. I am fine with this class average also because grading I had to only do accordingly. And remember one thing, today we were having interaction with third and final year students. From final year students, one major concern is that there only 2 students are having CGPA above than 8, because of which companies are not shortlisting them. So below 8, companies are not shortlisting. See, last year situation was good because good number of companies visited. This year, less number of companies are visiting, recession. So it will be reflected in terms of number of job offers. They will put more stringent criteria, and majority of them are not able to sit in the placements. Tell me final formulation. I need pi 1 equal to rho d square mu mu square into delta p. Okay, correct. What about pi 2? Again 1 hour. Sorry? D mu. It should be mu by rho Vd, then only Reynolds number will come. So mu by D is in the numerator or denominator? Denominator, okay. So mu by rho dV, that is pi 2. What about pi 3? So learn from others' mistake. If you also want to do same thing in the final year, then that is also okay. Tell me, quickly tell me now. See, you have, just from experience also you can say, you have only L as the parameter. What is the length dimension which will be non-dimensionalizing it? L by D. Once you will be doing practice, then only intuitive approach will also come. If you don't do practice, then stop this culture of studying in the last hour. Okay? People are suffering because of that. Those who are in final year, they are suffering. They are now saying they are feeling more load because they have to prepare for interviews also. So please. So ultimately, my I have got the 3 dimensionless quantities, and my interest is that delta p, I want to see its relation. So ultimately, I will be keeping delta p as the output parameter. So I will be writing pi 1 is equal to function of pi 2 comma pi 3. So I can say that from here rho d square delta p by mu, rho d square delta p by mu square equal to function of Reynolds number and L by D. Okay, so my first part is solved. Let me go to the second part now. So this is my first part. Now second part is, then plot this function using the following data for 3 pipes and 3 fluids. So in this question, what they have done, they have provided us the fundamental data for all the variables like diameter, length, discharge, pressure drop, density, viscosity and velocity. Okay. By using this data, what I have to do, I have to find out the corresponding values for the obtained dimensionless variables. Okay, so I have to calculate the values of pi 1, pi 2 and pi 3, and then I have to plot this. Okay, so in the next slide I have given you the plot. So you can see this pi 1 is along ordinate and Reynolds number was nothing but your pi 2. Pi 2 is along abscissa. Okay, and what was the third parameter? Pi 3, which was equal to L by D. So this third parameter L by D is having different values of L by D. So all these data are plotted over here. You can see for L by D equal to 200, this is the corresponding values of pi 2 and pi 1. So this is your data point. This is another data point. Okay. So now you can clearly see earlier how many data points were there? 9 rows and 7 columns, 63 data points. It was extremely challenging to plot the 63 data points. Now, after doing this dimensional analysis, how many variables you have now? 3 and 9 different conditions. So it means only for each condition, each data point. Okay, and all these data points you can simply plot on a two-dimensional plot. Okay, one parameter is along abscissa, other is along ordinate, and the third parameter is coming as a fixed parameter having individual value that I have represented with this L by D. Okay, so my part 2 is also solved. Now let's go for the part 3. In part 3 it is given that suppose it is further known that delta P is proportional to L. So till now from dimensional analysis we have come to know that pi 1 is equal to pi 2 function of pi 2 comma pi 3, where pi 3 is my L by D. But now it is given in the question that delta P is proportional to L, which is quite true for long pipes with well-rounded entrance. If you have long pipe with proper rounded entrance, then typically pressure drop is proportional to length of the pipe. Okay. So use this information to simplify and improve the pi theorem formulation. So we have to use this information and we have to improve the pi formulation and plot the dimensionless data in this improved manner, and then we have to comment on the results. Okay. So now what I can do simply, when I have written this function of Reynolds number and L by D, because I have come to know that delta P is proportional to L, so I can write this functional form simply as rho d square into delta P by mu square is equal to L by D times function of only Reynolds number. Is this point clear? Because L by D has to be directly proportional. So for L by D I have known the functional form, but for Reynolds number I don't know the functional form yet. Okay. So from here if I simplify it further, so this whole quantity is nothing but pi 1 and L by D is pi 3. So I can say that pi 1 by pi 3 has to be function of Reynolds number. So now I will be plotting pi 1 by pi 3 as function of Reynolds number. Okay. So that is what I have done in the next slide. Sorry, in this slide only, if you see the left ordinate axis, this pi 1 by pi 3 is the parameter and this is the Reynolds number. So when I am plotting this, all these scattered points have clustered together on a single line. Okay, and this is forming a straight line, and of course this is a straight line on a log-log plot. So if this is a straight line on a log-log plot, then by mathematically this should give us nothing but a power law relation. Okay, so that is what this relation is given, that pi 1 by pi 3 can be written as equal to 0.155, which is intercept, this particular intercept, times Reynolds number, which is calculated considering D. What is the meaning of RED? When I was writing RE, now in this particular column you have two length parameters. One is length of the pipe and other one is diameter of the pipe. So whatever the Reynolds number we have obtained, that is considering diameter of the pipe as the length scale. So that's why I am writing it as RED. Okay, and this is being scaled with scale of a power of 1.75. So this is coming close to a popular relation of Blasius. Blasius was Prentel's student who in 1914 by doing experiments obtained that for turbulent flow pressure drop is through the pipes is nothing but proportional to velocity power. Pressure drop is proportional to velocity power 1.75. So this is nothing but some other form of the Blasius outcome. Whatever the outcome Blasius has obtained, same thing we are obtaining from this particular data. Is this one clear? So this, with this example actually you can see the complete understanding of the dimensional analysis, how it helps. First we are having the dimensional variables, then we non-dimensionalize, then from non-dimensionalized data also by taking some hint from the plot of the data and physics of the problem, we can obtain a single relationship which will be applicable for all Newtonian fluids, and it will be giving us the relationship as a function of pressure drop and Reynolds number of the pipe. Is this one clear? So that is the benefit of the dimensional analysis, and it is significantly important particularly for the experimental measurements. When you have the experimental data, if you have to present experimental data, then we require this, we take the help of dimensional analysis to do that. Okay. Okay, so now from the next lecture we will start the next unit.